Alright, welcome to the final part in this little video series on control of the rotary pendulum. It's part 8, we'll talk about sliding mode control. So, sliding mode control is known to be a very robust control method. That will be useful today because this system has this disturbance, the cable here that acts like a spring that we have spoken about. It also has some static friction, which means that which makes it quite difficult to do very accurate position control. Sliding mode control is often referred to as model-free, although I don't particularly agree with that, at least not always. It's a high gain controller, so it uses a lot of effort to reach where it wants, but it uses that in a particular and non-linear fashion. Very often it's a discontinuous control, so it switches from one extreme to the other very often. And we have some documentation on sliding mode control here we can visit. So you can read up on our features here if you would like. But instead of reading documentation, today we will have a look at an actual example. So the procedure you have to go through when designing at least a simple sliding mode controller is you design something that is called a sliding surface. So it's some function of the state x that should equal 0 along the sliding surface. And then you choose a control law that drives the system there. So the control law is the function of this sliding variable. So it should ideally be 0 at the sliding surface. But outside the sliding surface it has some non-zero value. For a simple position control system like this, so you say that we are interested in controlling the arm angle, and the pendulum here is just a disturbance, so we just want to position the angle of the arm, and then this is just messing with us and making that difficult, and this cable is also messing with us, and the friction is messing with us. For such a system, a sliding surface that looks like some time constant times the velocity plus the position. That is typically a good sliding surface. And we can choose this time constant here. And then we pair that with a controller minus k times the sign of the sliding variable. So we see that this controller only has two possible outputs. It's either plus k or minus k, depending on the sign of the sliding variable. So it's kind of an extreme all or nothing kind of controller. So these two parameters, tau and k. Tau is the time constant. It determines, we choose this, it determines how fast the controller is trying to make the system move. And k determines how much effort the controller will use to make that happen. Typically we choose k large enough to overcome any kind of input disturbances. So this cable can be seen as an input disturbance. It adds a force or a torque to the arm, just like we control with a torque. So we must choose k large enough to overcome whatever torque this here implies. We also need to select k large enough to overcome the static friction. So in practice we need to overcome both of those. And maybe once we have selected k large enough there, we can tune a bit up and down to make the controller behave well. And that's essentially it. So we will try to use such controllers to control the system, and we'll compare it to a PID controller. So here I have a little function that runs this experiment. It has a standard setup of data logging. It starts each experiment by going to the home position. Then we have the control loop. We measure and we compute finite difference approximation of the velocity, and then we call the controller, and we have two different versions here depending on if we send a PID controller or a sliding mode controller, but they do more or less the same thing. All right, then we have my sliding surface. So here we see I have this I said tau times the velocity plus the position. So here, instead of having 1 over 7 here, I just set 7 here. So this is my tuning. This is I select the time constant of 1 over 7 here, and that makes the system behave reasonably well. This one is actually not used anymore. And we have my sample time, and we have a reference function. So here I have designed an interesting reference that just starts out by taking some steps up and down, and then it has a smooth sinusoid, so we can compare some different kind of tracking behavior. I run for 15 seconds. I allow a maximum control input of 3. And the first up is the PID controller. And here I have selected some parameters, the proportional, integral, and derivative gains to make this system behave reasonably well. So with more time, I could probably make this behave better. But this kind of simulates how control design takes place on the factory floor, out in the field, where you don't have a very accurate model of the system. You're just tuning the gains slightly, and PID controller is very often used for that. So now that was done, and we see a plot. We have the position in red, the reference in the top plot in red, and we have the actual output in orange. And we see that the PID controller is not doing a very good job. And I have actually spent a fair amount of time trying to tune this. I haven't used any model. I haven't used a model-based procedure, which if I do have a model, obviously I should use that. But here I haven't. I've just tried to tune by hand. And this is more or less the best I could come up with without spending too much effort. We see it significantly overshoots. It takes a long time before it reaches the actual reference here, and it's kind of sluggish in following the sinusoidal reference. We see when it takes a step here, it uses a large amount of control signal, so I could tune that away if I wanted to. We see that it has a small amount of noise, not too much. All right, the next step is to try sliding mode controller, and this is the most vanilla sliding mode controller, where the sliding surface is, where the control signal is some constant times the sign of the sliding variable. All right, so we can try that. And we see that this time it's pretty quick, but I don't know if you can hear that, but it's a bit noisy. So I can actually hear this thing shaking a bit now. And I think we will see that when we plot. And we see in the tracking plot here, we see that it has a much better tracking performance. At least it doesn't overshoot, and it doesn't take time to come back to the reference here. But then when the reference changes, it's somewhat sluggish here. And then when we look at the sinusoidal reference, we see that in the beginning it has a bit of a transient, but then it actually does a better job at tracking the reference than the PID controller did. But the price we pay for this is, look at the control signal here now, the yellow control signal here in the bottom. Unfortunately, the colors are not matched here. We see that it's plus or minus 0.4 or something here. And that's the only mode it has, it's either plus or minus. So that's obviously why I could hear the motor making noise here next to me. And that's very often undesirable. For mechanical systems like this, if you send in a signal that looks like this, you might cause excessive wear and tear on if there is a gearbox in here. And that's undesirable. Also, if we can hear it, it's sometimes unpleasant. So we can try to improve upon that situation. And we can improve upon that by making this sine function slightly smoother. So instead of a hard sine, we use a hyperbolic tangent with some kind of hardness parameter here, which I've tuned to 3. So let's try that. It runs again, and this time it's slightly more quiet, even though I can still hear it. All right, we see the plot here. So in the top plot, we have the dark trace here. We have a slight stationary error here. Otherwise, it behaves more or less the same as the vanilla sliding mode controller. And we see here in the bottom plot that the control signal action is much less pronounced now than it was with a standard sliding mode controller, but it still uses a lot of switching up and down. So before we are happy here, we will try a final version of the sliding mode controller called super twisting sliding mode controller, and that here you don't in fact choose a controller that's built into it. You just choose one parameter here, and I've tuned that to 0.2. So we try that. And this time the process is rather quiet. It's about the same as the last controller. Let's see how it behaves. All right. So now we have the blue trace, the light blue trace here. We see this slight overshoot, but it comes back fairly quickly. So it's definitely better than the PID controller here. We see that it's a bit quicker. It's as quick as the PID controller going down, but it has a much better performance here in the transient, in the steady state phase than the PID controller had. And it's also better at tracking the sinusoidal reference than the PID controller, roughly the same as the other two sliding mode controllers. If we look at the control signal action here by the super twisting controller, it's comparable to the smooth sliding mode controller. To quantify that, we can look at the control signal action. So here we just take the standard deviation of the control signal action. For the PID controller, 0.3, sliding mode controller, much more, or slightly more. If we look at the plot here, we actually see that the PID controller uses much larger control signal during the step transient here. So that's actually what causes the standard deviation to be bigger. It's a bit less noisy later. The smooth sliding mode controller uses the least amount of control action, and the super twisting is somewhere in between. If we look at the tracking error though, we see that the PID controller actually does better than the sliding mode controllers, at least the two first sliding mode controllers. And this is in large part due to the faster transient here when the step arrives. If we just look here, obviously the sliding mode controllers are a bit better. But if we now look at the super twisting sliding mode controller, we see this has actually the best tracking error as measured if we measure the standard deviation. So this is obviously a trade-off. The sliding mode controller is easy to tune. Somehow it's easier to tune than the PID controller, at least tuning by hand. If we had looked at also the pendulum angle, which we didn't do in this case, I find that the sliding mode controllers have slightly less oscillation. They take a bigger swing with the pendulum when they move, but then they have slightly less oscillations when they stabilize. Alright, so to summarize, the sliding mode controller is kind of an easy and model-free way of reaching a robust position control of a system like this under the influence of somewhat nasty disturbances at least. For more complicated systems, the sliding mode controller is more difficult to tune. But for simple systems like this, where you just want a robust alternative, it's a reasonably good choice. All right, thank you.